Let's begin exploring what I think is a very important and underappreciated aspect of circuit analysis, and that is circuit symmetry. And to begin our investigation, let's look at a simple circuit here, a two-port device, like a transmission line is a two-port device. But instead of a transmission line, we have a network that is made completely of lumped elements, specifically resistors. So this is a very simple circuit. It has an attribute, though, that is important and interesting, in that it has a plane of bilateral symmetry, otherwise known as reflection, a plane of reflection symmetry. And what that means is that this circuit, when we look at it in a mirror, would look exactly the same. It's congruent under reflection. We got a 100 ohm resistor here, we reflect to their side, and this 100 ohm over here, well, we still have the same circuit. Certainly if we take this 200 ohm resistor and we flip it around, we still have a 200 ohm resistor. And hopefully you see if we can rotate this 50 ohm resistor around just to reflect it around, it's still a 50 ohm resistor. Again, we say the circuit is congruent under an operation of reflection across this plane of bilateral symmetry. Now, this idea of bilateral symmetry is ubiquitous in nature. Many animals, organisms exhibit bilateral symmetry. Humans, for example, have a plane of bilateral symmetry. On the outside, we're more or less have reflection symmetry. If you look in the mirror, you'll get confused about what is your right hand and what is your left hand, because they each look the same to you. On the inside, of course, we don't exhibit bilateral symmetry, but on the outside, certainly we do, as most animals do. If we look at it in terms of human structures, we see symmetry that occurs quite often. Symmetry has a nice aesthetic appeal. It also has a lot of engineering application with respect to maximizing forces and such, keeping the forces in equilibrium in civil engineering structures. But also in electrical engineering, we find many of our circuits and networks that we devise and are useful have bilateral symmetry. It's not that we necessarily wanted for them to have bilateral symmetry, but in the process of designing and developing useful devices, it turns out that they have bilateral symmetry, again in a way that a civil engineer often finds that a structure with bilateral symmetry is optimal in some sense. So again, this bilateral symmetry can be defined by a plane of reflection symmetry. And across that plane, we find each side is the mirror image of the other. And structures, again, of this type, we say have bilateral symmetry, and they will simplify, or can simplify, our circuit analysis. Now, in this particular circuit, we have a little bit of a problem in that our plane of reflection symmetry bisects two of the resistors. We have a 200 ohm series, or a 200 ohm resistor on top that the plane bisects axially, and then a 50 ohm resistor at the bottom that the plane bisects laterally. And so what do we do to simplify this? Well, we know the circuit rules associated with resistor. If we take a axial resistor and we cut it in half, then we've shortened its length, and the resistance is directly proportional to the length of that resistor, and so we've cut its resistance in half. So in other words, if we take a 200 ohm resistor and we slice it in half and break it into two resistors, we have 100 ohms on each side. This is just our series rule. 100 ohms plus 100 ohms brought together gives us a 200 ohm resistor. And so that's what we're going to do here on this top part. We're going to slice this 200 ohm resistor in pieces and spread it apart. So now we have 100 ohm in series with 100 ohm. And we can see that this division has preserved bilateral symmetry. We could have taken the 200 ohm resistor and of course split it into a 50 ohm resistor and 150 ohm resistor, but that would have destroyed our bilateral symmetry. If we put 50 on one side and 150 on the other, then the circuit would not be a mirror image of each other. But by dividing it into equal halves, we've preserved that bilateral symmetry. Same thing, of course, when we split that 50 ohm resistor laterally through the resistance. The resistance of a resistor, if you recall, is inversely proportional to the cross-sectional area. And so if we slice it this way, we have halved the cross-sectional area, which means that we have increased the resistance. The pipe has gotten smaller. We've increased the resistance by a factor of 2. So we take the 50 ohm resistor, we slice it laterally and break it into 2 pieces. Now we have two 100 ohm resistors that are in parallel with each other. And of course, again, this is our rule that we know from circuits. If we have a situation where we have a 50 ohm resistor, that's simply two 100 ohm resistors in parallel with each other. Parallel rule creates two 100 ohm resistors in parallel and makes a 50 ohm resistor. Again, we could have done this other ways to get the same two dissimilar resistors to come together and have 50 ohms, but we wanted to split in a way where the two sides are equal, so we preserve this level of bilateral symmetry. Again, we look at this, we still have a mirror image across this reflection symmetric plane. Now, why do we want to do this? What's the point? So we recognize circuits have bilateral symmetry, that have reflection symmetry, and we simplify them to preserve that symmetry so that we can analyze those circuits in a more straightforward and simpler way. It doesn't seem like it would be necessarily true that we could do this, but hopefully you've had some experience with this in electronics. If you ever looked at a differential amplifier that had a level of bilateral symmetry associated with it, a reflection symmetry, and if you recall there, we went through and analyzed that circuit with respect to common mode and differential mode. And we're going to do the same thing, and we can do the same thing in our microwave circuits. So let's consider this case. We take our two-port device and we're going to connect an ideal voltage source on one side with the value VG, and we're going to connect another ideal voltage source on the other side. To preserve the bilateral symmetry, we need to make sure that these two voltages are exactly the same. VG here is the same as VG here. If this is 10 e to the j pi, then this is 10 e to the j pi. So by doing so, we have now put sources that create voltages and currents, but we have preserved our bilateral symmetry in our circuit. And so the question we ask ourselves is are the currents and voltages created by these symmetric sources on the symmetric circuit, do they exhibit any level of symmetry? We go through and we define every current and every voltage in our symmetric circuit, and we define these voltages in a way that likewise that are consistent with that symmetry, that we maintain that symmetry. So, for example, the easiest one to kind of see is currents. I have I1A on this side, and on this side I'll define a symmetric current I'll call I1B. And notice the current is positive, defined I1A is defined as positive when flowing from left to right. I1B is defined as positive when flowing from right to left. And by doing it in this way, we preserved the reflection symmetry. If we were to go through and reflect across this plane, I1B would come over here and I1A would come over here, but these two arrows would still be pointing each at the plane of bilateral symmetry. In contrast, if I go through and I write I1A is positive and moving from left to right, and I1B is positive and moving left to right, both arrows would be pointing toward the right. And if I took a mirror image of that, then we'd find that in that case, both arrows would be pointing to the left. We would have destroyed the symmetry associated with these notations. Again, we want to make sure when we rotate across the plane of reflection, everything looks the same as it did before. And so we need to do the same thing with voltages. Notice I have plus to minus for V1B across this 100 ohm resistor. Here I have plus to minus for V1A across this resistor. This plus reflects to this plus here. This minus reflects to that minus there. So I go plus minus on one side, and then I go minus plus on the other. And so the reflection symmetry is preserved. Now, for currents that flow tangentially to the plane of reflection symmetry, we need to preserve consistency in the symmetry by, if we have one current that points downward parallel to the plane of reflection symmetry, when it reflects across, that current likewise needs to be pointing downward. So again, these are mirror images with respect to the notation. Same thing for voltages. If I have plus minus on one side, that's tangential to the plane of reflection symmetry, I need to have plus minus on the other. Plus on the top on both sides, minus on the bottom. And so by going through here, we look at this and we see we have a perfectly symmetric circuit. The only thing that's different is the currents and voltages on this side I've called A, and the voltages on this, currents and voltages on their side, I've called B. Now, let's say we didn't have notations here, we just had values. If we went through and we rotated the whole circuit, if we reflected the whole circuit across that plane of reflection symmetry, we'd have exactly the same circuit. We couldn't tell the difference. If I had to turn around and close your eyes, and I may or may not have reflected the symmetry, the circuit across the plane of reflection symmetry, and then I had to turn around, you wouldn't be able to tell whether I had or had not. And from that, we conclude that the currents on either side of this plane of reflection symmetry, in the way that we've drawn the notation, must be equal to each other. Likewise, the voltage on either side of the plane of reflection symmetry must be equal to each other, because everything about the circuit is symmetric with respect to this plane. That extends to the voltages and the currents on either side. Right away then, we've made a big dent in analyzing the circuit. We've been able to come up with 9 different equations associated with these currents and voltages. Again, this is all based on symmetry. This IGA must be equal to IGB. V3A must be equal to V3B. I1A must be equal to I1B, based on our symmetry arguments and our symmetry arguments alone. But we start looking at these currents, the I1A and I1B, I4A and I4B, and finally this I5A and I5B. We look at this and we say these must be equal to each other, yet it seems like Mr. Kirchhoff would have a different opinion about how these things should be related. Because from KCL, this must be true. I1A and I1B must be equal but opposite each other. They must be related by a -1, or a phase of 180 degrees, pi. Likewise for 4 and 5. Every time we have a pair of arrows that are pointing at each other from either side of the reflection, plane of reflection symmetry, we find by KCL that these equations must be true. Yet, by symmetry arguments, we said that these equations were true. We didn't say that I1B is opposite of I1A. We said I1B is equal to I1A, for example. So, how do we resolve this contradiction? Is there any way to resolve this? Well, it turns out both equations, both sets of equations, are correct. Both sets of equations have a constraint on what those currents must be. By symmetry, these 3 things must be true. By Kirchhoff's law, KCL, these 3 things must be true. And there is a way, only one way though, where both sets of 3 equations can be satisfied. The one solution is that all the currents must be 0. If I take 0 and multiply by -1, I still get 0. And so the only values that will satisfy all 6 of those equations on the preceding page are if all 6 of those values are equal to 0. And so this is the situation we have in our circuit, that each of these currents are equal to 0. And if we look at this, it says that there is no current that is crossing this plane of bilateral symmetry. And you think about it, this makes perfect sense. Because we have a perfectly symmetric circuit, there cannot be a source side and a load side. We can't have one side of the circuit where it is delivering current at a given rate, or charge at a given rate, current flowing from one side to the other, or the other side back. There can't be a source side and a load side. And because there can't be a source side and a load side, that they're equal, the only way we can preserve that is if there is no current flowing from one side to the other. There's no imbalance that can be created in the circuit by having current flow across this plane of bilateral symmetry. The statement that the current flowing across the plane of bilateral symmetry is zero is really the same as saying that this plane of bilateral symmetry, this plane of reflection symmetry, acts as an open circuit. It's not physically an open circuit. There are still wires that cross it, yet we have a situation where no current can cross that plane. It acts as an open. We call it a virtual open. The plane of symmetry has become a virtual open circuit because no current can pass through it. So since the plane of bilateral symmetry is effectively an open circuit, we've broken the wires, or might as well have broken the wires. It won't affect the circuit since no current is flowing through it. We can go through and sort of take the circuit and snip it into half along that plane of reflection symmetry and separate it into two pieces. And notice again, this won't change the circuit at all. We didn't have any current flowing across the plane of bilateral symmetry anyway, and so it's effectively the same as cutting in half with open circuits there at the end. This will make the circuit analysis much easier and simpler. This is the benefit of recognizing symmetry in circuits. We have no current that flows here, and that by itself will make the analysis of this circuit easier. Also, we see that this circuit on this side and this circuit on the other are exactly identical. Again, if I took one and reflected it across, I'd find they are the same circuit. All we have to do is analyze one half of the circuit for each current and voltage, and we know then the corresponding current and voltage on the other side will be precisely the same. That was the argument that led to this virtual open. And so again, the circuit that we have is only half of what we had before, and because we have a lot of zero currents, the analysis will likewise be easier. A key to doing this successfully and making it very easy to do the analysis is to recognize, again, what happens to the circuit when we put these virtual opens here. We have no current flowing. These three currents are equal to zero. And in that case, it makes this circuit very easy to analyze. If this current I1A is equal to zero, then there's no current through this 100 ohm resistor, and then therefore V1A is equal to zero, as is V1B, the corresponding voltage on the other side. Because these two currents are equal to zero, then by KCL we find that this current is equal to I2A is equal to I3. What we have really that's left in the circuit is simply two resistors in series connected in parallel with an open circuit or an ideal voltage source. And not only are they connected in series, they're equal value of 100 ohms, and so we can go through and quickly do a voltage division to find the voltage across each of these two. V2A is 1/2 VG, V3A is 1/2 VG. Finally, this current that flows through them are easily determined by Ohm's law. It's simply VG divided by the sum of these two resistors. Since they're in series, 200 ohms, VG over 200. And those become then the currents that we have in the circuit on either side. And likewise, the voltage V2A and V3A, again, is VG over 2. Same for the corresponding voltages on the other side. So when you go through and cut your circuit in half and you apply your virtual open, it's important to kind of stop and look at the circuit that results and think about all the manifestations. It may be a very complex looking circuit until we apply the virtual open, and then all of a sudden things get very simple. Essentially, again, what we have here is a voltage source in series with two resistors of equal value. Now we attached two ideal voltage sources to either side, either port of our two-port device or symmetric two-port device, and if they were exactly the same value, we preserved that symmetry. But they didn't have to be ideal voltage sources. We could, as we did in this case, attach two identical current sources to each of the two ports of our symmetric two-port device. We could also attach more general sources, Thevenin's and Norton sources, that would have source impedances or source resistances associated with them, and we could do that as well, as long as each side has precisely the same source impedance. So if RG on one side is 10 ohms, RG on the other side must be 10 ohms as well. In addition to the open circuit voltage, they must be the same. We have to attach identical sources on either port. And again, these could be ideal current or voltage sources, or Thevenin's and Norton are really any kind of circuit on one side I could attach to that port as long as I attached its reflection symmetric version on the other. So if we look at the circuit with the ideal current source on there, this becomes very simple once we've separated our two half circuits with the virtual open here. Again, these three currents must be equal to 0. And so what we have now is a current source in series of two resistors. And so the current through each of these resistors is Ig. The voltage across each of these two resistors is Ig times 100 ohms. And since, again, this current is equal to 0, that voltage is equal to 0. And so we can go through and very quickly analyze the circuit and come up with these results. And notice for every result there's another corresponding result for the other side of the circuit, the other side of the on the other side of the plane of virtual of the plane of reflection symmetry rather. And so every time we get an answer, we're actually determining two. Now we're going to try something slightly different. We're going to put two voltage sources on either side of our symmetric circuit, and each of those two ideal sources are going to have precisely the same magnitude. But one of them is going to be multiplied by -1. In other words, the two sources are going to be precisely 180 degrees out of phase with respect to each other, e to the j pi, or -1, plus Vg minus Vg. If I looked at the two sources, I would find one has a magnitude, it's an oscillation of a certain magnitude. The other has an oscillation of the same magnitude. If I look at them both together, again, they're going to be oscillating with the same magnitude, about 180 degrees out of phase. Now, what does that do to our results? It turns out, if I have a voltage here, that's the same magnitude as the voltage here, but the phase is 180 degrees on one side than it is on the other, that result will exhibit itself throughout the entire circuit. Any current that we identify and its corresponding symmetric circuit on the other side will find the result for this particular situation where the voltage sources are equal but opposite is that the results for the currents at any 2 point that are symmetrically related will likewise be equal but opposite. In other words, have the same magnitude but be out of phase by 180 degrees from one side to the other. That will exhibit itself at every single point within this circuit. A circuit of this type we call a circuit with odd symmetry. In the previous case, we had even symmetry, where every voltage and current had the same magnitude across the plane of reflection symmetry and had precisely the same phase. Odd symmetry, they have the same magnitude across the plane of reflection symmetry, but they are related, they are out of phase with each other by 180 degrees. Again, we call this odd symmetry. We're using the same current and voltage definition as we did before. Current and voltage definitions that are consistent with respect to the plane of bilateral symmetry. So we have not changed those at all. But because we have sources now that are equal magnitude but opposite in phase, each one is related to each other by a -1, we find again that that will ripple across and exhibit itself at every pair of current and voltage in this symmetric circuit. In other words, I1A right here must be equal to the opposite of I1B. Equal magnitude, 180 degrees out of phase. This voltage V2A and this voltage V2B are no longer going to be equal to each other as they were for the even mode analysis. They are going to have equal magnitudes but a phase of 180 degrees. They will be 180 degrees out of phase. They're related by a -1 or e to the j pi, and that's true again for every pair of currents and voltages in this circuit. The problem now we're going to run into is when we look in voltages like this one, V3A and V3B. We look at these two and we, of course, notice that Dr. Kirchhoff would have something to say about their relationship as well. So if we look at these two voltages, from Kirchhoff's law, we would say that these two voltages must be equal to each other. But because we have sources with odd symmetry and the circuit itself is symmetric, we come to the conclusion by the symmetry argument alone that these two voltages must be equal but opposite, that VA3 must be equal to V3B -1. So how do we resolve that problem? Well, this is the same problem that we saw for even mode with respect to currents on either side of the plane of bilateral symmetry. We have two statements that seem to be contradictory, but there is a way they both can be satisfied. There is a way that this is true, which Dr. Kirchhoff's requires, and this is true, which our symmetry arguments require. And just as before, they can both be true only if both of these voltage values are equal to 0. 0 is equal to itself and also equal to its opposite of itself, equal to 0 minus times a minus 1. And so by saying these two things must be true, and we have valid arguments for each of these statements, we are saying that this solution has to be the solution when we have an odd symmetry in a circuit with bilateral plane of bilateral reflection. What this means is, as we move along this plane of reflection symmetry, this plane of bilateral symmetry for the circuit, we find that the voltage cannot change. The voltage, the potential difference between 2 points on our transmission line must be precisely the same. So that the difference cannot be anything other than 0. This then forms something we call the virtual short as we move and measure the voltage between 2 points on the on this plane of bilateral symmetry. We find that that difference will always be 0. The voltage between 2 points must be 0. Moreover, we can make an argument, since we have Vg on one side and minus Vg on the other, to preserve this odd symmetry, that this voltage value must be 0 with respect to these. However we define these two voltage sources, the value here must be 0 with respect to that. And of course, in this case, they're connected through this conductor here, and so this value, all of this conducting structure, becomes what we call a virtual ground. It has a value that is 0 with respect to the sources. And again, we can make an argument that that has to be true to preserve the odd symmetry. It's easiest to see probably if we make these DC sources, which we could. Let's say this was 10 volts and this is minus 10 volts. Well, the voltage along this value could be constant, but if it were 4 volts, let's say, well, that would sort of bias itself toward the plus 10 and away from the minus 10. Or if it was a minus 3, again, that would sort of mess up the balance and be more similar to the minus voltage and the plus voltage. The only way we preserve this odd symmetry is if this point right here in the center must have a voltage that is 0 with respect to define how we define these two voltage points, and those two voltage points are both defined with respect to this line right here. And since the bilateral plane of bilateral symmetry crosses this, this becomes what we call a virtual ground. So strictly speaking, it's a virtual short. The potential cannot change, the voltage cannot change along this plane, but more generally we call this a virtual ground and call that voltage a value that's numerically equal to 0 with respect, again, to the voltages, all the other voltages on this circuit. Again, this greatly simplifies our analysis. If we have this odd symmetry structure in our circuit, we can apply a virtual short or virtual ground along the plane of reflection symmetry there. And again, it's important to note, once you do that, to simplify your circuit. Notice what happens here. For example, what we've done is short out this 100 ohm resistor. We have 0 volts across that 100 ohm resistor. If we have no volts across the resistor, we have no current flowing through that resistor. Effectively, what we have here in a circuit is a voltage source in parallel with two 100 ohm in series rather, with two 100 ohm resistors in parallel. This 100 ohm and this 100 ohm, notice they're each connected right here on one side, and now because of the virtual ground or the virtual short, they're connected on the other side right here, and that goes to ground, which then controls the loop. So we have Vg in series with two 100 ohm resistors in parallel with each other, and that's what really all this circuit is at this point. Once we've shorted out this resistor, these two resistors are in parallel, but you need to recognize that when you get your circuit. So draw your half circuit, apply your virtual short, but then simplify that circuit, and you'll find oftentimes what looked like a very complex circuit will turn into a very simple circuit because of the virtual short. Oh, finally, I guess I should say, we can analyze all these values, and if you do, you get these results. Now, the important thing is, again, just like in the even mode, once we get one answer, we're determining another answer. But remember that the answer is equal but opposite. So if I say that I1A is equal to VG over 100, and that's equal to minus I1B, what we're really saying here, remember, is I1B is equal to minus VG over 100. V1B is equal to minus VG. I5B is equal to, in this case, it would be equal to a plus VG over 50, since we have two minus signs there. So make sure you get that right. Sometimes students will kind of stumble at this point and not get their minus signs right. So be careful how you generate your second set of solutions for the remaining odd mode half circuit.